Hi, my name is Ducasse, and I'll present you the result of my master's thesis, which is entitled Benchmarking Quantized Neural Networks with FIM. So this work was made in collaboration between the ENSTA Bretagne and the Labstick, where I'm currently doing my PhD, along with Pascal Cotteret and Loïc Lagadec. And on the other hand, the Heriot-Watt University, where I did my master's thesis with Mr. Robert Stewart. So in this talk, I'll go through the background of quantization, quantized neural networks, and how we can port them onto FPGAs. Then we'll go through the workflow and benchmark of our experiments, which will go through Brevitas, ONNX, FIM, and talk more widely about our methodology. And finally, we'll go through the results in terms of accuracy, the impact of quantization, the impact of parallelization, and open up on the potential future works of the project. So first, I'll talk about the AI and energy consumption. So as we all know, the AI basic block is a neuron which basically consists of several inputs to which we'll apply some weights. So they are in red here. And those weights will be updated and modified throughout the training so they can perform better. Another thing is the activation function, which is in green. That is usually a nonlinear function that allows for a simple network to perform well on nonlinear data. So to put it briefly, training and using a neural network is basically composed of two main phases. The first phase is training, that is used to update the weights. That can be done on a powerful to very powerful setup once, and usually only once. While on the other hand, inference, so the action to test an input using the fully trained network and the final weights, should be able to be performed on low-resource architectures for every new input. So this operation has to be performed again for every new input. So now if we look, on the other hand, at energy consumption of several basic operations, such as add, multiply, or memory reads, we can see, for example, with the 8-bit add, that it consumes 0.03 picojoules of energy, whereas its 32-bit floating point counterpart consumes 30 times more, 0.9. And the same basis can be applied to look over the area of the reads and the multiplies. So basically, the higher the precision, the higher the energy consumption and area costs. So if we look at optimizations for neural networks, we can see that several ideas emerged in the latest years. So one of them is compression, which basically remarks that there are several redundant weights inside of neural networks, and then we can simply use one occurrence of each with a proper hash function to redirect the need for a given weight to its actual storage. Another idea could be pruning, where we see that there is a lot of redundancy, and rather than grouping redundancy, we can simply remove it by pruning either synapses or neurons directly. And the last one that will be our focus is quantization. The weights and activations are usually 32-bit floating points or 64-bit floating points, and we can reduce them to 8 or 16 bits, or even less, by using scaling and thresholding. So for example, here in the table, we can see that the value of 0.136 could be represented with varying precision from 1 to 8. And this is usually done by using the different thresholds that the precision allows, and to map and round the actual value to one of those thresholds. So this is what is done for the weight, and this is what can be done to activation functions as well, with, for example, this hyperbolic tangent function. One thing to note, however, is that the higher the precision, the higher the number of thresholds are needed in order to round the actual 32 or 64 bits to its 8, 16 or less bits counterparts. So now if we look at quantized neural networks in current frameworks, we can look at Google TensorFlow with TensorFlow Lite, which allows you to write an arbitrary integer quantization bit widths from 2 to 16, and also provide an automated conversion from 32-bit floating points to 8-bit integers, as well as quantization over training and post-training static quantization. The same thing can be said for Intel Distiller, where you can use arbitrary bit width quantization and an automated conversion of pre-trained networks to custom precision. And PyTorch has released a quantization package where you can either convert pre-trained networks from 32-bit floating points to 8-bit integer, but you can go beyond. So you can't use sub-8 bits bit widths. So we can see that there is a clear demand for quantization or reduced precision, and its associated gains in both space and energy for the end architectures that will host the networks and perform the inference over and over again. So now if we look at frameworks for QNNs and FPGAs, we can ask why choose an FPGA for artificial intelligence. And one of the main reasons is the high throughput and low latency that it provides. And it also helps the developers and development team to increase the value and cost through reconfiguration. This means that you can quickly prototype and tailor the actual architecture to your needs due to its reconfigurable nature. Moreover, it has a low power consumption and a rather low cost when compared to ASICs, for example. So if we look at why we could port machine learning on hardware, there are two main focuses that would be the accelerating the training phase or accelerating the inference phase. And this can be done using the inherent customizable precision of the FPGA since it's all reconfigurable. The objective being keeping correct accuracy results. So if you look at frameworks that have been developed to port QNNs and FPGAs, we can see as early in 2016, YODA-NN, FCN, and FPGA ConfNet were all released, but their source code was closed, and development apart from FPGA ConfNet has been stopped. In 2017, FIN was released with being open source, and its development still being active as of today. And later on, REC-YOLO, that is more focused on the object recognition, and TinyCNN were released in 2018 and 19, but they both have their code source closed and their development stopped. So there is a lack of open source frameworks and benchmarks between them, and this table shows that out of simplicity and accessibility, we chose to use FIN to perform our experiment because it was open source and in active development. So if we go through the workflow of FIN, we'll first go through the first step, which is training. So from our network model that we can design in Brevitas, which is the training facility for QNNs and works as a drop-in PyTorch replacement. This means that you can simply use the Brevitas layers instead of the actual PyTorch one, and even use them both together, and it should still work. This Brevitas model, once trained, is then exported to an ONNX intermediate representation, which is an framework-agnostic intermediate representation that Brevitas will use with custom annotations. This representation, once annotated, will be given to FIN, which is a hardware compiler that will perform transformations on the ONNX IR, then convert it, prepare the network before building the hardware representation synthesis and deploying it up to the FPGA board. And the FPGA board has Pink, which is a Python image for FPGA, and is ready to host the end network. So if we take a closer look at Brevitas, This is the definition of a quantized LeNet network. We can see that there are several well-known layers, and each of them has a specified bit width, so either 8 for the activations or 4 for the weights, but this can be changed as the developer pleases. So Brevitas implements a set of building blocks at different levels of abstraction to model a reduced precision hardware data path at training time. So it features arbitrary precision for both weight and activation, separately or all together. It provides quantization-aware training using the thresholding technique that I showed earlier, and it generates a custom ONNX representation with custom annotations that are needed for sub-8 bits representation and that are needed to simplify things for Fin later on. ONNX is an open standard for machine learning interoperability and is basically a framework agnostic intermediate representation of neural networks. So it stores both the type, the inputs and output sizes of each layers, as well as the weights and different attributes that Anilia can hold. And it's used to export from the different development frameworks or import from existing neural network model banks or pre-trained models. And it can be extended with custom annotations, custom operators. And moreover, you can simply resume the training by importing a given ONNX model with any framework. And along with ONNX, you can visualize your network. So here is a LeNet 5 network, along with Netron, that allows you to check for correctness in terms of layers, in terms of types, and it can allow you to annotate your network. So if you take a closer look at Fin, so Fin is receiving the ONNX model and will perform two sets of transformations. One of them is network preparation related transformations, and the other ones are related to hardware build. So the first ones are, for example, basic transformations such as renaming, checking the sizes of the inputs and outputs, checking the different types. The next one is a streamlining transformation, which combines different layers all together and removes, for example, the need of a multiply layer and add layer with a simple thresholding method that is described in the Fin paper. And next, the layers that can be converted to HLS are converted to HLS, and the other ones are set into another partition. So the graph at this moment is a mixture of HLS and non-HLS layers. Then Fin will go through a folding part where the developer can adjust the sizes of the P in SIMD and basically set the parallelization of each layer of the network and adjust it so that it fits the best its end architecture. And next we'll go through the hardware build transformation, so the IP creation, where Fin will design one HLS IP per layer and then stitch them all as the whole network. It will then create the Vivado project, perform the synthesis, and deploy the bit file on the end card. And finally, the execution flow will go through a parent graph that will either execute the layers on the board for those that could be converted to HLS and execute the rest with ONNX exec. So to assess the impact of quantization, if we look at previous studies, so this one from Baxter et al., so it showed that the hardware utilization and memory utilization goes along with the precision used and the bit width used. So here with activation bits going from 1 to 8 and weight bits going from 1 to 8, you can see that the higher the precision, the more resources will be used in terms of LUTs, flip-flops, or block ramps. In the same vein, Su et al. Presented the NIST classification on a simple multi-layer perceptron, as well as cipher-10 classification on VGGNet. And we can see the same tendency for highest precision to have the lowest throughput and use the more computational resource as well as memory usage. So it raises several questions of what is the impact of quantization? So here we have a hunch of what it might be, so both in terms of accuracy and hardware utilization. But we can also wonder what is the impact of parallelism. Is there an impact on hardware utilization and throughput if we adjust the parallelism correctly? And it also makes us wonder, is custom quantization useful? Is there an impact of sub-8-bit precision in terms of both hardware utilization and accuracy? So this is the methodology we use to train our different experiments and deploy them on the board. So we use the simple multi-layer perceptron on the NNIST and facial NNIST datasets, and we trained them for 100 epochs, and we changed the learning rate at epochs 1995. So we changed the weights bit width from 2 to 8, and the activations bit width from 2 to 8 as well. So this gives us a total of 49 iterations that we'll refer to as AXWX. For example, A to W2 for the network with 2-bit precision for weights and 2-bit precision for activations. And finally, we only deployed the A2W2, A3W3 extra up to A8W8 onto the pink Z1, which is the board that we targeted. So if we have a look at the accuracy on both NNIST and facial NNIST, we can see that the weight bit width seems to have an impact that is far greater than the activation bit width. So on this one, we see that we can still process through the training for 100 epochs. But if we look at this graph specifically, we can see on the left side that the activation do not seem to impact the end accuracy as much as the weight can. And another thing that we'll learn is that if we look, for example, at the 3-bit weights on the NNIST dataset, we can see that. So we can see here that with 100 epochs, we can reach the same accuracy than the 8-bit A8W8, for example, representation and training after 40 epochs. So accuracy is linked to the weight bit width, and training can cover up accuracy gaps with enough epochs. So now if we look at the hardware utilization, so both in terms of logic and memory, we can see that the lower the representation, the less logic and memory is used. And moreover, we can see on the right side with the RAM18 that hardware utilization grows exponentially due to the successive thresholding for activation quantization. So now we'll have a look at the impact of parallelization. And if we look at the different configurations, so A2W2, A3W3, and A4W4, with varying PE and SIMD, so 2, 8, and 16, we can see that the results are more or less the same, apart from the fact that we couldn't deploy the A4W4 with 16 and 16 as PE and SIMD, because it was too large for the board. So one reason that might be behind those numbers being so close is the size of the network that is really small, only consisting of 3 layers and 2 activation functions, but also the fact that we're comparing 2, 3, and 4 bits. So on the right side, we've varied the PE and SIMD for the A3W3 configuration, and what we can see is that there is no clear separation between the impact of the number of PEs and the impact of the number of SIMD. So it depends on the configuration that you've chosen, but in our case, using 16 and 16 brings nearly a 62 speed up of throughput for our given configuration, going up to 372 images per second. So throughput and DRAM bandwidth are tied to the parallelization factors. The higher the P in SIMD, the higher the throughput and bandwidth. So to have a look over these different results, we can conclude by saying that accuracy is linked to the wait bit width way more than the activation bit width, and that training can cover up accuracy gaps with enough epochs. So we saw that in our case, 60 epochs more could make a 3-bit precision network perform as well in terms of accuracy as its 8-bit counterpart. Throughput and DRAM bandwidth are tied to the parallelization factors, and the higher the P in SIMD, the higher the throughput and bandwidth. So this means that you have to tailor your parallelization so that it uses the most out of your end architecture. And harder utilization grows exponentially due to the successive thresholding for activation quantization. This means that you have to choose your quantization carefully if you go beyond 8 bits, because this means that it will use a lot of memory in terms of thresholds in order to round the values to their corresponding 2 or 3 or 4 bits counterparts. So in our case, to determine the best configuration, we looked after accuracy and throughput, and in our case, A3W3 with P and SIMD set to 16 offers the best throughput with up to a 62 times speedup over the 2 and 2 P and SIMD configuration, and the best accuracy with enough training. So this is a comparison between the 8.8 configuration trained after 40 epochs and our 3.3 representation after 100 epochs, for example. So a discussion has to be made over those results, however, because we simply used a simple data set, which is MNIST and fashionist, and a simple, very simple neural network, which is a simple multi-layer perceptron. So as future works, we plan on developing or integrating more networks into our frameworks, quote unquote, and add more data sets and try to see if the tendency of using the best PE and SIMD going for 3 bits, for example, will use the best out of the end architecture. And finally, it would be interesting to see if those results persist outside of FIN. So, for example, compare it to FPGA ConvNet or the different possibility in TensorFlow Lite or Intel's distiller. So, thanks for listening to me, and if you have any question, please feel free to ask.